So to compensate this for this last lecture, which was too theoretical and dry, this one now is more practically oriented, and I'm going to explain some things that then you're going to do on the tutorial. So this is part theory to explain how to work with TensorFlow and Tensorboard. We'll continue looking at TensorFlow and look at Tensorboard too, and then also explaining the exercises that you're going to do in the tutorial afterwards. So first we're going to take a brief look at graph modes, just very brief. We're not going to focus on that in this course, but this is just so we can build the graphs to see on Tensorboard, and I'm going to explain also what Tensorboard is. Then we're going to look at some issues with numerical stability when we're training our models, and look at some exercises. So we're going to start with a simple example of logistic regression, and then we're going to look at logistic regression for classification, but then we're going to look at regression to predict the miles per gallon of different automobiles from a set of features. And we're also going to look at multiclass classification. So we're going to look at binary classification, regression, and multiclass classification. And multiclass classification will be with the MNIST dataset, which is for handwritten digits recognition. So this is a classical dataset in machine learning. So let's see first what Tensorboard is. This is a suite of visualization tools that you can use to examine your models, to monitor learning, and to basically have a neat interface for visualizing what's happening with your models. We're going just to look at a few features, but this is always Tensorboard is in development, so you can accompany using the programmer's guide and online tutorials and so on if you want to go into more details. The idea for this course is just to get you started and to understand the basics of how to use Tensorboard. So we're going to first create a folder where we're going to output the Tensorboard summaries. So the way Tensorboard works is that it looks for a logging directory when we start Tensorboard, and inside that folder expects to find one different folder for each run. So we need to generate a new folder whenever we train our model or something like that. Otherwise, if you store everything in the same folder, then the plots will get all messed up, mixed together, and things will be a mess. So one simple way of doing that is we use the datetime module, and format the datetime with year, day, hour, and so on, minute, second. So we have a timestamp string that is different every time we run the script. So when we run our script to train our model, we set a root directory for the logs, for example, logs, or you can set in another folder, so on, but this would be in the same folder as the script, logs. And then inside this one, we create a new folder. So the folder where we're actually going to store our logs will be the root folder, the root directory for the logs, and then something, for example, model or experiment or something that you want, and the timestamp after that. This way we get a new folder every time we run our script. You don't need to do it this way, but just remember that if you log more than one run in the same folder, then things will be a mess in Tensorboard, and it will be hard to understand what's there. Now we're going to use the logistic regression model, so the same we used last week. And what I'm going to do is show you how we can output the graph, the computation graph, into Tensorboard so we can visualize our model. So first we need to build the model, and by the model I mean basically this part. So we have the variables, the parameters that we're going to adjust. In this case, it's one column of two variables for the weight. So basically, this is one neuron, or a logistic regression in 2 dimensions, and then the bias variable here. And also part of the model is what computation we do with the parameters to output the prediction. So basically, this would be our model, the variables and the prediction, which is we multiply the weights by the input, add the bias, and then apply the sigmoid activation function for that. In eager execution, the names of the operations are irrelevant. But if you are going to output for the graph, you can put names there and make the graph a little prettier. We're going to see some examples of that later. But now we're not going to just save the model, we're going to save everything, the whole computation graph. So we're going to have here the logistic loss function too. So this is that loss function where we take the class and multiply by the logarithm of the prediction plus 1 minus the class and multiply by the logarithm of 1 minus the prediction, and this would give us that logistic loss function that we then average over all the examples to get our result. And also the gradients. We'll put the gradient computations into the model, so we'll write the whole graph. And so we define here the gradient function that, remember, uses this auto differentiation algorithm that TensorFlow has. We use this class gradient tape, the context of this class, to get them to trace all the computations. So this will call the prediction function. The tape will trace the computations in the prediction, and then the logistic loss, and all these computations will be traced in order to compute the derivatives, and we return the derivatives and the variables that we want to apply the derivatives to. So this is basically the computation graph that we're going to use to train the logistic regression. And now what we need to do is, so far we've been running this with eager execution. That is, whenever the interpreter finds these operations, TensorFlow will put everything it needs in the GPU or whatever hardware you have and execute them. And then it will move on to the next one and so on. So this is not as efficient as it could be if we could give TensorFlow the whole computation graph in one go, and so TensorFlow could optimize and distribute all the computations between the different processors and the hardware that you have. So one reason for using eager execution is that it's a lot simpler to implement and intuitive, because it's just like you're programming in Python. One reason for using graph execution is that if you give the whole graph to TensorFlow, it can optimize better. However, in our case, we are not going to worry about the performance of learning, and in any case, next week we're going to shift to the Keras API, which is a more higher level, and it takes care of all these things internally. So we are not going to delve into the graph mode of execution, because that will would require a lot of detail on the TensorFlow, and we don't really need that for this course. So the only thing we're going to use here, and this is for two reasons. First, so that you know how to output the graph to Tensorboard if you want to visualize your model. Another reason is that you know that this thing exists. So if you need to use it, then at least you have a starting point and you can follow up from there. So we have this autograph algorithm in TensorFlow, which can convert Python code, trace the Python code, and convert into the graph language of TensorFlow, where it can be compiled and implemented in the GPU, CPU, whatever hardware then it's used. So to use autograph, we have this implemented in the TF function, in the TensorFlow function wrapper. So basically, you give a function to this function, and this function outputs a new callable object that has worked out everything it needs to implement the graph. One easy way of doing this in Python is instead of explicitly calling this function with your own function as an argument, you just use this decorator here, and this tells the interpreter that when you're defining this function, actually what you want is to send this function to the TF function and receive whatever the TF function is giving you. So this is the basic idea. And what happens here, and this is the magical part, is that when TF function receives our function, for example this one, create graph, the only thing we're doing here is we are receiving two tensors. We are calling the grad function, so this one here, and we don't even care what it returns because we just want to call the function. What the TF function does, and this is the autograph algorithm, is to trace all these computations. So grad will call prediction there, and then it will call logistic loss. So all these computations will be traced and the whole graph will be produced, including all these gradients and so on. So by calling this grad function, we are telling TensorFlow with this algorithm to trace all the computations and generate the graph in memory. And this is what we're going to do to create our graph in Tensorboard. So we're going to create a writer. This is an object that writes to the logs of that Tensorboard can read, and you just use this create file writer from the summary module and specify the folder. Remember that this folder logdir is generated based on the timestamp, so it's always different when you run your code, and it will be stored in a different place. Then we send this writer to the write graph function here. I forgot to put the additional line, but it's just we call this function with x and y just so it's able to call everything else. So this is our data that we loaded. You saw this in the last week, but basically it's the gene data we used in last week. We separate the y values, which are the labels, from the x values, which are the features, and we standardize the features. Okay, so now we have this, and when we create the graph, we convert these NumPy arrays into tensors, because it's a good idea to have everything in tensors there, otherwise some things may not work. So we're going to assume that everything in our computation is in tensors. We convert before calling the function, and we call create graph. It creates all the graphs, and then we use this as default method of the writer with this context to save the trace. So basically, when we do trace on, TensorFlow will keep track of all the graphs that are generated from this point onwards until we either disable trace or we export the trace to Tensorboard. So this is basically what you need to do to save your graph. Create some auxiliary function that uses autograph, that uses the graph mode to trace all your computations into a graph, and then tell the summary module, this trace on, to export everything to Tensorboard. So use trace on to say from here on, whatever computations are traced, you store them in the graph. You call the function to create the graph and then export to the logs. So if we do this, we get the results. We can see our graph. We are not going to be looking at autograph in more detail, but you can see this is a good page for seeing how this works. So in the TensorFlow guide, and how you can use it to improve performance. But this will be mostly used if you have to do some strange models that you cannot implement in Keras easily, and also you have many operations that you really need to compile into a single graph to optimize as much as possible. For the kinds of problems that we're going to solve, and in particular because we'll be using Keras a lot, it's not necessary to delve into the autograph, so this would be outside the scope of our course. And for this course, we're only going to use the TF function, so the autograph algorithm, to create the graph to represent on Tensorboard. Other than that, we won't be using it more. So after you do this, if you run this code, note that I missed here a call to write graph, but it's just after this line, you just have write graph with the parameters. And after you do this, then you have in your folder, the log folder, you saved the summary of your model and the representation of your model, but now you need to run Tensorboard. So Tensorboard comes with the TensorFlow installation. You should have it installed. Just go to your shell prompt, go to the folder where you have your log directory. This would be the most practical way, or else you can give the full path. But what you have to give here, you call Tensorboard, and the logdir parameter will be this folder here that you created. So this, the root folder here. It's the folder where Tensorboard will look for subfolders where you have the different computations. So after you do this, you get a message that Tensorboard is running, and Tensorboard, the interface is through the browser. So it's an HTTP server that's running locally. So you access it with the local host, and it's in this port, 6006. It's easy to memorize because it looks like Goog from Google. So that's why it has this number. And when you interface with Tensorboard, so you use the browser, you can go to the graph tab there, and you can see the graph that was generated. You cannot see very well here in this image because it's a bit small, but you see that you have here the matrix multiplication, the sum of the bias, and then all the things to compute the logistic loss and the gradients and everything else. So you see this then ends up being quite complex because not only you have the loss function there, but also all the gradients from the auto differentiation algorithm that is looking for all the derivatives and keeping track of them all. So this is basically the look of the graph that we generated. Now we can also add values to Tensorboard, and this is one of the useful features in Tensorboard because it allows us to keep track of training. As you add values to the logs, you can also keep refreshing, or it refreshes automatically Tensorboard, and you can look at how your model is training online. So let's do the training loop. This is what we did last week. We have the learning rate. We're going to use a batch of one example at a time. You can change this. You can use batches that are larger. And then we're going to shuffle everything in each epoch, create the batches. Note that these batches, I am converting them into NumPy, into TensorFlow tensors. So remember this, that by default, all the operations you create with TensorFlow expect a floating point with 32-bit precision, and NumPy matrices have 64 bits. So we need to convert from our matrix to 32 bits and then create a tensor from this, and send this then to the grad function to compute the gradients and apply the gradient. The optimizer is unfortunately not here. I forgot to put it here, but it's the same we used last time, the stochastic gradient descent. We'll be looking at more optimizers next week, but for now we're always going to use that one. So remember to create the optimizer first and then do this. So here, this is what we do for one epoch. We run through all the batches, and at the end we can compute the predictions for the whole training set, and then see what is the training error. So we call the logistic loss function, we get the training error, and now here is where we add this to the Tensorboard logs. We use the writer object, and we add a scalar object here, which is just a number. And for every time you add an event to the Tensorboard logs, you need to indicate what is the step. This is particularly useful when you're adding numerical values that you want to plot in a sequence. But you need to do this all the time. So even if when we are creating the graph, we have to put there step 0, because this is also an event when we are exporting the graph. So this is what we get. We start to see the results on Tensorboard. Training is going nicely, and then things go wrong. So these triangles here are not a number, And I think some of you tried to use this logistic regression model at home, and you reported this problem. So this was really on purpose. We are trying to implement the logistic loss function in a way that is a bit naive, and so we get numerical instability. After a few epochs, say 20, 30 or something like that, we start getting these results, and from this point onwards, then everything is basically ruined. So by the way, this NaN is not a number, which is what you get when you do operations like dividing by 0, or you get a floating point underflow or overflow, something like that, and then the arithmetic code just writes that this is no longer a number and it cannot work with that. So the reason for this is our implementation of the logistic loss function. So prediction is the result of the sigmoid activation, which is this green one here, and it tends to 0 for minus infinity and to 1 for when we go to infinity. But it never reaches that value. It always approaches 0 as we go to smaller and smaller values. And then we are taking the logarithm of this sigmoid function. So the logarithm approaches minus infinity as we approach 0, but of course we cannot take the logarithm of 0, so it should never reach there. And in theory, the sigmoid function would never reach exactly 0, and the logarithm would then not have an input of 0, so it would never go explode to infinity. But as you can see, when we're dealing with numerical computations, this is just a disaster waiting to happen, because all it takes is just a small rounding error somewhere and this explodes. So we cannot really use the logistic loss function implemented like this because it's too unstable and eventually it starts going badly. There are ways of solving this problem. For example, there is this technical report from 2012 which has this approximation. Basically, you can see that the logarithm of the sigmoid function starts becoming linear after this point. So if you have a very large negative number, 33.3 or something like this, then you can just use the same number. When you take the logarithm of the sigmoid of t, just use t. And then you have these other approximations. This is the logarithm of 1 plus the argument, and so forth. So by using these approximations, it's possible to compute these functions, the logarithm of the sigmoid, without running the risk of things exploding. In TensorFlow, what you get is not computing the logarithm of the sigmoid, but going one step forward and computing the whole logistic loss. So this whole thing where we compute the logistic loss, it's computed in this way. So x is the net output of the neuron before going into the sigmoid activation. So this would be the linear part of the neuron, and z is the target label, 0 or 1. So this way you get, with this expression, you get the same as if you first apply the sigmoid to x and then write all this expression, but with the advantage that you don't get these numerical problems. So fortunately for us, we don't have to actually implement this. We just use a TensorFlow implementation of sigmoid cross entropy. I put sigmoid twice here, I shouldn't, but this is sigmoid cross entropy. It's this function here. Well, there's actually one function called sigmoid cross entropy in the losses module that uses this one. So here for illustration, I'm using directly the one at the bottom of the stack. So this one is called sigmoid cross entropy with logits, and the reason for this is that what you get here is the logit, which is the name given to the linear output of the neuron. So this is before you put in the sigmoid activation. So what we need to do is to change slightly our code. For the predictions, we need the sigmoid activation because we need the output to be between 0 and 1, gives us the probability and so forth. But for the logistic loss, we actually just need the logit or the multiplication of the weights by the input plus the bias, and no activation added. So just the linear part. And now we change the logistic loss function. It now receives the data, the features, the X matrix. It computes the logits for that for the activation, and then it uses the sigmoid cross entropy with logits function from TensorFlow and averages over all the batch. Now this part here, this reshape, you saw this problem last week. I'm not entirely sure if it's necessary here, but since this is so often gives problems when you try to implement this at a low level, I generally just do the reshape when I'm computing the loss, because at this stage I'm expecting one vector of activations, one value for each example, and one vector of labels, one value for each example. If you're expecting matrices and so on, take care, especially when you're using, for example, softmax activation and so forth. So don't just reshape at random. Think about what you have. But in this case, I want to have them as vectors to make sure that it doesn't happen that I have, for example, the labels in a vector and I get the logits in a matrix, and then there is some problem with the computations. So this is the change. Now the grad function simply calls the logistic loss function with x and y, and the logistic loss function does everything in order to use this implementation of the sigmoid cross entropy in TensorFlow. And now this works because now this is numerically stable. We just need to change a bit this part, the loss computation here, because now we have to give the x values and the y values to the logistic loss function. But other than that, everything now works well, and we see our model training without having those not a number errors. So basically, you have loss functions in TensorFlow. You can use the ones in the losses module. I use the lower one in the neural networks module because this one comes explicitly with the name with logits, which is what we are giving it here at this stage. But these ones also work with logits, so basically they call the other one and they don't have, so these two work with logits and call the other one. The mean squared error, you can also use this one, but mean squared error does not have these numerical stability problems. So whether if you're just playing with TensorFlow, if you compute the squared error yourself, it's not a problem. It's these two, so the sigmoid cross entropy when you're doing binary classification, and the softmax cross entropy when you're doing multiclass classification, that really have that problem of applying logarithm to sigmoid activations. And so you should use the TensorFlow implementation because it's more resistant to these numerical instabilities. So let's see an example of regression. We have this automobile mile per gallon data set. You have one version of this data set that I removed some categorical columns and empty rows without date and so on, but you have also, you can look at the original at the UCI repository, but basically this is data on the year of make, and other features of cars, and we want to use that to predict the efficiency of the automobile, so the number of miles per gallon that the automobile can travel. So some things that you should do: shuffle the data before splitting into training and validation. So now we're going to start worrying about overfitting. We're going to look at validation sets. So first, shuffle everything because we don't know what criteria were used to order the examples in the file. Then we have the target in the first column, which is the miles per gallon, and we're going to standardize everything. Now this is for those of you who did the machine learning course, probably you remember, but those who didn't, it's useful to standardize the values that we are using, because if we have problems with numerical problems with large numbers or different scales and so on, In classification, we standardize the features but not the class labels, because the class labels are discrete, are just different labels for the classes. It makes no sense to standardize them. But with regression, it's also useful to standardize the target values to avoid having to deal with very large values or very small values. And then we store the scaling factors that we're using for standardization, in order, when our model outputs a prediction, that we can convert into the appropriate units. So when we standardize, we are not dealing with miles per gallon anymore, but then we revert everything with the output if we want to give the user our predictions. So this is what we're going to do. There are 392 examples. Use 300 for training and the rest for validation. And remember, the last neuron should have only a linear output, because we're doing regression. We don't want to restrict the output of the neuron. And in regression, we are going to use the mean squared error loss function for training. Now, for the exercise, you can try different activations, learning parameters, and so on. I'm just going to give a brief overview of the code. So for this part, when you're doing this in the tutorial, you can follow the lecture. But my advice is that you try to do as much as possible for yourself and just look at the code when you get stuck. So this way you can try to get more confidence and more familiarity with these things. So we're going to load the data. This skip rows is just to skip the headers on the TSV file. If you want to open the TSV file, you can to look at what the different features are, but we're not going to bother too much with that for this exercise. Then we're going to shuffle and standardize everything. So standardization means we subtract the average of each feature and divide by the standard deviation of each feature. And that's what we're doing with the axis 0 here, because it's computing the mean for each column and the standard deviation for each column. We're going to keep these values, the means and standard deviation, because if we need to use our model, we need to revert this scaling back to the original units. Now we're going to take the validation data above the 300, so the last 90 something elements, and the training data here would be the first 300 examples. Then we're going to create our model, so we can start with we're going to do a multi-layer perceptron. So we can start by creating some auxiliary functions that help us create a network. So this would be a function to create a layer. We say what is the size of the input. So what would be the input, so that we can get the shape, the number of columns, and know how many input values, how many weights each neuron must have. And also we want to know how many neurons per layer. So this will be the shape of the weight matrix, one row per input, one column per neuron. Also the bias variable will have one value per neuron. We're going to start with a normal distribution for the weights here. The bias can start at 0, but remember that we need to break this symmetry when we initialize the weights. So this would be to create a layer, and it returns a tuple of weights and biases. And now we can create a network. We give the network a list of the number of neurons in each layer to create a multi-layer perceptron, and the network simply loops through this list and stacks new layers. And it will create the network, which is a list of tuples with the weights and bias. Here, the weights and bias, and also a single list, a flat list with all the variables that we're going to use later for the gradient, to apply the gradients and to compute the gradients. So this is just an auxiliary function that allows us to create a model by just saying how many neurons we want in each layer. Now we're going to create the prediction. This is the rest of our model, which is the actual computation. And so we're going to start with the first layer. We are going to input the x values, the features. We're going to do the matrix multiplication, add the bias, apply a leaky rectified linear unit as an activation, and skip on to the next layer. So we keep adding layers. So actually this is a bit of a leftover for something I'm going to show later that I didn't delete. I'm going to delete now. Okay, so we just keep going through these layers and computing the activation with a leaky rectified linear unit and passing on to the next layer. And we do this all the way until almost the end of the network. So we stop at the one to the last layer, because then the last layer we just do the matrix multiplication and we do not add any activation. So this is because we are doing a regression, so the last layer will be naked at the end and just have the linear part, the linear activation. And now we're going to create a graph to look at our model. We're not going to include everything, the loss function, the gradients and so on, because that will create a very big mess. We just want to look at our model. So we're going to use again the TF function to trace these computations and create the graph, but instead of calling the gradient function, we're just going to call predict. So we have this model in our tensorboard log, and we're going to do the same thing as before. We're going to write the graph by using the writer, and so the writer here is a global variable that we need to create, and then we export the trace into the logs. So this way we can look at the how our model looks like. So we have the matrix multiplication and adding the bias for the first layer. Then we have matrix multiplication and adding the bias for the second layer, and so on until the third layer. And here we have the rectified linear unit activations in the first layer and the second layer, but not in the last layer. However, this is not a very elegant way of representing our network, because we are just putting everything together, all the computations, and looking at the whole graph without a neat structure. We can improve things by using this name scope in TensorFlow, which allows us to group operations into groups with names, and also by giving names to the operations. So we can say that this, after we multiply and then we add the bias, this will be the net output of the linear part, and then we call relu the activation, and we put for each layer everything in a name scope which has layer and the number of the layer. So layer 1, layer 2, and so on. This is why this variable was there that we increment, and we add these groups of operations as layers. So this is exactly the same thing, the prediction function, and then we also add a layer to the a name to the output layer, and we are doing exactly the same thing, but we are adding names. When we are actually running our model and training our model, these names are irrelevant, because with eager execution, names are ignored. But when we run the graph to create the graph for Tensorboard, in that case, names are used, and the result that we get is like this. So you have layer 1, layer 2, layers, the output layer, and then we can actually click the layer and see the values there, the matrix multiplication, the net, and the relu inside the layer. So if you want to create more elegant diagrams of your models, you can do this. When we start using Keras, Keras also does this automatically. So in practice, this will be useful if you actually have to do something more in detail with TensorFlow. But in general, it's just for you to understand what is happening when Keras is representing your models and putting them in Tensorboard. So once again, we start training, and we're going to find a numerical problem here. So if you do things like I've shown this far, so with this code, if you implement this, you're going to start seeing not a number again, even if you use a small learning rate for the stochastic gradient descent and these parameters here. And this is a different problem, not numerical instability due to the implementation of the loss function, but due to the initialization of the network. So far, we've been using simply the normal distribution to initialize the neurons, because when we're using sigmoid activation, this is not a very big problem. It may interfere a bit with the learning if you get too large values, because then the slope of the derivatives tends to 0, but it doesn't give you these instability problems. For rectified linear units, that's not the case, because you can have very large outputs from the neurons. Then when you compute the quadratic error, it gives you a very large error with a very steep gradient, and then stochastic gradient descent starts to diverge instead of converging towards the solution. So in general, we need to take care with weight initialization. We're going to look at more sophisticated methods for initializing weight later on. But for now, this is just to call your attention to this problem. So I advise you to first implement things like I show here, see that they don't work, and then look at the difference when we scale back the weights of the neurons. For example, we can divide the weights of the initialization of the weights of the neurons in one layer by the number of neurons in that layer. So to do that, you just add another argument to the random normal from TensorFlow, which is the standard deviation. And instead of using the default, which is 1, you can use, for example, 1 divided by the number of neurons. So if we have a larger layer, the initialized weights will be closer to 0. This is just a quick fix. We're going to see more sophisticated methods for initialization next week. But for now, it seems to work as long as you don't have a very large learning rate. And so you can train like this. Just a small detail for practical purposes. We are computing the loss function, which is the mean of the squared error. So note that the squared error, the mean of the squared error, will give you in units that are the square of miles per gallon, which is something that is not very intuitive. So if we compute the square root of the mean squared error, we get back to the original units, and now we just have to rescale our error by the scaling factor that we used in the beginning when we standardize everything. So remember that when we were standardizing everything, we compute the standard deviations for all the columns in our data set, and the first column was the miles per gallon. So the first element here in this standard deviations vector is the scaling factor that we used to divide our original data and get it to a more reasonable range. So now if we want to see our error in miles per gallon, we just need to compute the square root of the squared error and then multiply by the scaling factor. So this way, training error and validation error will be in the units that we expect, and we can use that to interpret the results. So for the exercises, try different architectures, monitor train and validation error, fine-tune the parameters, play around a bit with this. You'll see that sometimes it will start diverging. You're getting that not a number problem, reduce the learning rate and things like that to solve that problem. So finally, these parts are basically tutorials because you have everything explained here in the lecture, just some few extra details for you to experiment with. For this part, I will let you a bit more on your own. So this is the modified MNIST dataset of handwritten digits. This is with 28 by 28 pixels for each image, and you get zeros, ones, twos, and so forth. And you can download this data set through TensorFlow. So basically, what you're going to import Keras, that high-level API, and from this MNIST data set, you load the data. So when you load the data, you get the training images and the test images. And if you don't have this data on your computer, the MNIST will download. So do this with an internet connection, and the first time you run this code, you'll probably have to wait a bit to download the dataset, but afterwards it's stored in your PC, so then you can use it as many times as you want. So first we need to reshape the data, because this is a three-dimensional matrix, which is a stack of images, and we're going to put it in 2 dimensions. So each example having 784 features in a row. And we're also going to split these 60,000 images in the training set. We're going to use 50,000 for training and 10,000 for validations. So if you want, you can use the layer function from the regression example. So to stack and the network function to stack all the layers. But remember that now we're going to use softmax cross entropy for the losses, because this is a multi-class classification problem, and softmax for the probabilities, for the predictions. Remember also that softmax cross entropy function must receive the logits, not the output of the softmax activation. So you need to have one output of the network computed for the loss function and a different one for the predictions, like we did with the logistic, the sigmoid cross entropy. Another thing is that these labels that you get, so the train labels and the test labels, are integers from 0 to 9, which correspond to the actual digits that you have here. But softmax for multi-class classification, what you need is to have 10 outputs, output neurons, and then attribute a probability to each of the classes. So you're going to need to do one hot encoding for your data. One hot encoding is this form of encoding where you have one element in the vector for each of the classes. So in this case, these vectors have 10 elements, and you put a 1 in the class for this example and a 0 in all the other classes. And this is what we want our softmax output to approach. We want our softmax to be high on this class and low on the other classes here. This is easy to do because you have a function, this two-categorical function in the Keras utils. So all you need to do is you take the labels that you want to use for validation or for training, and you pass them through the two-categorical function, and what you get on this side is a matrix like this. So remember that now your labels are not a vector, they are a matrix with one hot encoding, and this is what you're going to compare to the softmax activation. Once more, also to remember, when you're actually computing the loss function, you're not going to explicitly have the softmax activation, but you're going to give the one hot encoding labels and your logits to the softmax cross entropy function. So for this exercise, I recommend that you look up on the net how to do this, what are the order of the parameters and so on. Remember, don't switch the order of the parameters for these functions, because one of them is the labels, the other is the logits. If you exchange them, you get incorrect results. When you want to measure accuracy, if you want to see if the predicted class is the same as the original class label, you can use you can convert the output into NumPy, for example, and use the argmax function. So this can tell you which is the position with the highest value on each of the rows, and this will correspond to the class label for the original. So this way you can extract the actual digit predicted by your softmax activation. So just to recap here, you're going to use this with softmax activation. You can compare different activation functions in the hidden layers. So if you use sigmoid with many layers, you probably bog down the training, but you can try rectified linear units, leaky, and so on. Try different network dimensions. So remember to check overfitting with validation data. I have an example in the lecture notes. I updated the lecture notes just before the lecture, and you have some examples there of how you can see this overfitting. But one easy way is, if you have your training error coming down while you're training the network and the validation error is increasing, then that means you're overfitting the data. So in the end, you can try optimizing this and look at this site where you have results of MNIST classification with different networks. Okay, so let's take a small break. We saw graph mode and tensorboard and these issues on numerical stability, but mostly this lecture is about getting you started now with the exercises using tensorboard and tensorflow and training your models. So let's take 10 minutes for resting a bit, and we'll start the tutorial in the Hangout, the same one as for last week, at 10 minutes past 6. Okay, so see you soon.